We're going to take a look at perchlorate next. And we had a whole bunch of different structures for perchlorate. The first structure that we have for perchlorate is where we didn't expand the octet. The only problem with this structure is the very high formal charges. The formal charges were a bit extreme. For example, on chlorine, we would observe a +3 formal charge. I mean, can you imagine taking 3 electrons from chlorine? Not easy, right? I1, I2, I3, that's a lot of energy. And so this is... let me just tell you, there are some Chem 1A instructors who say never expand the octet, just leave everything. And then we'll explain this using octet and ionic bonding. And so the degree of ionic bonding here would be significant because the -1 attracted to +3 is big. But because of the high formal charge, this structure is not totally accurate. In that sense, we've got to try to minimize that formal charge. But anyway, chlorine, let's just focus on chlorine here to save time because we've got so many structures to deal with. Chlorine's going to be what? sp3, 4 single bond groups. And so we're going to have 4 singly occupied orbitals on chlorine, and then oxygen's going to come in. And so oxygen comes in with what orbital? What's oxygen's hybridization? sp3. And so we have sp3 sigma bonds. And so we have 4 oxygens coming in to form these sigma bonds. And so to draw this is not so bad. We put the chlorine here and we draw 4 tetrahedral sp3 orbitals. This, 2 in the plane, 1 coming out, 1 going in. Each of these singly occupied. And then we have our 4 oxygens coming in here. So sp3 on oxygen. Oxygen coming in here, here, and here. Oxygens are also sp3 hybridized, so 2 in the plane, and 1 coming out, 1 going in. Okay, 2 in the plane, 1 coming out, 1 going in. And this one going behind, we'll just draw them all dashed because it's getting hard to write that in the proper perspective. This one coming up, we'll do 2 in the plane, 1 coming out, and 1 going in. Like that. So oxygen is negative, 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 +3. And so what we did was we increased the formal. Actually, we increased the bonding. We made more multiple bonds to get rid of this formal charge. In fact, if we did, what did we do? We, at the other extreme, this is structure 1, and then we had structure what? 4. Structure 2 is 1 single, 1 double. Structure 3 is 2 doubles. Structure 4. We came up all the way to structure 4. Structure 4 had 3, right? Had 3 double bonds, like this, and 1 single. This structure was kind of nice because all these formal charges are 0, and this has a negative formal charge. Each time we create a formal charge, it costs a significant quantity of energy. And so this whole thing is going to have a negative. And how many resonance forms did we come up for this? So we should have 3 other resonance forms, right? So altogether, there should have been 4. Is that correct? We did this earlier. Can you remind me? Yes? All right. And then we came up with a hybrid structure, where each of the bonds is a 1 2/3 bond, right? 1 2/3 bond in the hybrid. All the bonds are the same. Each one of these has 2 lone pairs fixed and 1 lone pair floating. Floating means what we call delocalized. The ones that are fixed are called localized. And so what I did was the dashed ones are delocalized. That is, that electron cloud is spread out over it. Whereas the localized ones, the electron cloud is spread. All right, the first thing is we do not do valence bond analysis on the hybrids. This is too difficult. And so for valence bond analysis, we pick one of the resonance forms. Choose one of the resonance forms. Because, you know, when we start getting, how do we show 1 2/3 bond in valence bond analysis? Then we have to start mixing more orbitals, and things get a bit more complicated. And we aren't going to do that. Okay, so we choose this. Let's just choose that structure right there. We just drew out. And so what we're going to have is something like this now. Chlorine, what's the hybridization on chlorine? sp3. And so we write out our 4 sp3 orbitals. How do we fill them? How many electrons does chlorine have in this structure? Count them up. 1, 2, 3, 4, 5, 6, 7. 7 electrons. And so we got to fill these orbitals with 7 electrons. So 1, 2, 3, 4. Now the 5th electron, should I pair it? No, because there's no pairs. So the 5th electron's got to go where? And so this is chlorine's 3rd period. So this is 3sp3. The next orbital is 4s. Are we going to put it in the 4s? No, we're going to go to the 3ds. And so 1, 2, 3, 4, 5, 6, 7. Five, six. So what do we have here? Well, what we're going to have is 1 oxygen is going to be sp3, and so this 1 oxygen that's sp3, all right here, the oxygen sp3 comes in, and then 3 oxygens are going to be double bonded to it, and so 3 oxygens. Well, what's the hybridization on oxygen? The double bonding oxygens. sp2. And so it's going to be an sp2, sp3 sigma bond here, followed by p, d, pi bond here. And then another oxygen is going to double bond. So it's going to be an sp2, sp3 sigma, and a p, d, pi bond. And a third oxygen is going to double bond here, sp2, sp3 sigma, and a p, d, pi bond. And so in this structure over here, how many p, d, pi bonds do we end up with? We end up with 3 p, d, pi bonds at what angle? this should be a tetrahedral structure. And so the 3 PD pi bonds should be at 109-degree angles to one another. And in fact, the angles are 109.5 in this, because it is tetrahedral. Well, are the d orbitals at 109.5 or are the d orbitals at 90 degrees? The d orbitals are 90 degrees. And so the only way we could get this is by significantly mixing the orbitals. Or, you know, in other words, there's going to be trouble because forming one PD pi bond shouldn't be a big deal. And so if we form one PD pi bond, it might look like this. Oxygen sp2, chlorine sp3. So we have our sp3, sp2 sigma bond. And then let's look at our PD pi bond. Here. And so we got a p orbital, let's say here, and a d orbital here. And so we got one PD pi bond here. Okay, where's the next PD pi bond got to come in? The next PD pi bond has got to be at a 109 angle. So let's put it down here at a 109 angle. Oops, wrong color. And so I got two sp3s in the plane. Okay, and then this is going to bond to an oxygen over here. And this oxygen is going to be sp2, sp3 sigma. Now, what I'm going to do is I'm going to put this oxygen in side view here. And so let's put this p orbital like this, in side view. And then let's make a d orbital here in side view, like this. Actually, maybe I shouldn't do purple. Let's do a different color if I have one. I do. Actually, I do have more colors. Let's do green. And so here's another d orbital like this. Actually, that's not the greatest drawing, but here's another d orbital, and here's that PD pi bond here. And this d orbital has to be at 109 relative to this d orbital here. And then I'm going to have another one, oxygen double bonding. I'll put this next oxygen that's double bonding out over here. And so I'm going to have an sp3 on chlorine bonding to an sp2 here. So here's my sigma, but how am I going to orient the d orbitals? Here. And so if I try to do the d orbitals here, maybe I'll put this p in perspective like this and then have another set of d's in red here. Like that. And so the point of this is to say this. Here's the point. Which structure is correct? Probably none of them. 1, 2, 3, 4. Probably what is correct is some kind of mix because you have some challenges here. One challenge is the original structure has too high of a formal charge. Costs energy. The other challenge here is this. You have in structure 4 where we got rid of all the formal charges, except for one. We have to have one because it's ion. We got rid of all the formal charges, but the d orbitals have to be in a contorted angle to one another. When you do these at a contorted angle, this is what a contorted angle looks like in terms of orbital overlap. Let's say I have a p orbital here. The next p orbital, if I want a good sigma bond, I'm going to bring it like this, right? But if the angle is contorted, let's say I have another p orbital here, is that good orbital overlap? You know, this would be like a bond AB. When we draw a bond, an A to B bond, do we draw a kink in it to indicate, wow, that's a kink bond? Is a kink bond going to have good orbital overlap? No, because the electron density is going up like this and going up like this. We don't have good orbital overlap. And so when we contort the angles, we weaken the bonds. Okay, the other thing is this. Recent quantum mechanical studies, this is at the end of chapter 11. Recent quantum mechanical studies have been trying to determine how much PD pi bonding there is, how much d orbital participation there is. And it's turning out that the d orbital participation isn't as much as one originally expected. And so a lot of people are saying that there's some degree of ionic character. And so the more we go towards structure 1, the more ionic it is, and the less d participation there is. The more we go to structure 4, the less ionic the bonding is, and the more d orbital participation there is. And what they've been finding from recent studies is it's a mix. It's somewhere in between the two extremes, and that somewhere in between is where the energy's been minimized, where we can lower the formal charge but not contort the orbitals too much. Does that make sense as far as mixing goes? And so this is why I called it a hybrid of hybrid, because we generated all these hybrid structures, and then we got to generate a new set of hybrids depending on what percentage structure 1, what percentage structure 2, what's the percentage of structure 3 and structure 4. And then we'll have some kind of, so it's not quantized in that sense, it's continuous range. And then in that continuous range, we have a percent D character in there, and we have a percent ionic character in there. And so a lot of people just ignore this, and I've been thinking maybe I should just do the same. Is a lot of people will give you a simple rule. The simple rule is get the formal charges minimized, expand the octet, do whatever is necessary. Or, you know, another handful of people will just say, okay, forget that, never expand the octet, always do an octet and high formal charges. But the reality is somewhere between, and I think you should be sophisticated enough to deal with that, you know. To help you deal with this, we're going into the computer lab. We're going to do some quantum mechanical calculations on some structures and then see, you know, what the hybridization is. And so that's going to be next week, okay? All right, so why don't you guys go ahead and get started on these remaining with the time left. For nitrate, you're going to just pick one of the resonance forms and do your analysis. Nitrate's the next one? Okay, do nitrate and see if you can do it, because nitrate's going to have a double bond in there as well.